Hi, I'm Chris Kanich, and this is CS361, Systems Programming. Today, in our series on how the internet works, we're going to be learning about why the internet even works, even on a good day. So our goal, if we're building the internet, is to build this super awesome global communications infrastructure out of a whole bunch of cables and switches and routers and stuff that we're just going to build. We're going to take those and we're going to turn them into that piece of cake, right? The trick here, the real big issue is that this is really ridiculously complicated. It's so complicated that we can't just have one thing that's like internet. Here's how you internet. Even before we get to the technical scaling problems, it's such a big issue that at a mental level, at like a system engineering design level, we need to split things up so that we as humans can actually wrap our head around the whole thing and complete a specific task. Today's question is, how do we provide all the different features of the internet across all of these different networks? Because remember from the last lecture, different network technologies can be connected through the idea of a router. So I got one network talking to a router who's a member of network A, and a completely different network B that has that same router on it using a different interface. And you want to be able to seamlessly send those messages from one point to another. So I've got an answer for you. The answer to this question is that we're going to use the separation of concerns, layering and encapsulation, and the thin waist of the IP layer to get all of this stuff done. And I could think of separation of concerns and layering and encapsulation as this idea of adding a layer of abstraction or a layer of indirection like we did with the virtual physical memory. But we're taking that approach and cranking it all the way up to 11 so that we can do this for all sorts of different ideas. We're going to say it was cool to have one layer of indirection. We're going to add several layers. We're going to have them all do completely different things. And that way, as long as everything fits together correctly and gets their individual jobs done, then we'll be able to do this really cool, awesome thing called internet. So there's a few different ways to talk about this layering concept. There's the 7-layer OSI model, which is important because it's standardized. But the one that I like to teach from that I think is a little bit more meaningful is the 4-layer internet model, where we have an application layer, a transport layer, a network layer, and a link layer. These different layers that were designed into the way the internet works allow us to separate the different responsibilities that are going to be taken care of at any given point in the process of providing internet so that they can do one thing or a few things and leave it to other layers to get swapped out or to switch from one to another to get the job done. One concept that doesn't usually get covered when we talk about the 4-layer internet model or even the 7-layer OSI model is the DNS, which effectively functions as another like special guest star layer that is required to even do any of the IP-related connections that you would do in a real modern network scenario. DNS is basically used to allow humans to remember memorable human language names for things that are named just using numbers so that it's easier to do. And this also provides another layer of abstraction where a human can say, here is the name called uic.edu. And today, uic.edu resolves to one IP address. But if I want to move my UIC web server to a different server, I can just change the mapping. I don't have to actually change the IP address of whatever machine that I'm moving the web server to. DNS is just as central to the way the internet works as these other 4 layers, even though you might not see it in other videos or in other classes. This is something that I think you should remember as just as important as anything else that's in this layering model. So the application point of view is kind of the highest layer of this entire set of layers. And this is what programmers are usually going to be dealing with on a day-to-day basis if they are doing network programming. But if you're doing network programming, you're probably going to be using some version of the socket API that we'll see a few lectures forward in this module. And we are also going to be using that for homework 5. We're going to be using this socket API to build a application that a user will derive some benefit from. The benefit might be looking at hypertext media and clicking on links and viewing other hypertext media from different servers, like with HTTP. It could be sending or receiving email, like with SMTP. Those applications are defined by whatever their designers want them to accomplish, and those are kind of the last step towards creating an application. But the great part is that you as an application developer only really need to understand your protocol. You don't have to have a really deep understanding of the protocols below it, but you do have to know a few important details. And that's the whole reason for this module. DNS exists as an application on top of a transport layer, built on top of the IP layer, but it doesn't require you to do any sort of bootstrapping where you know that you need to go talk to a machine with a specific number, with a specific IP address, and that machine will map every other name you've ever asked about to the IP address that you need to actually connect to using the socket API. Now, the transport layer more or less implements the functionalities that the application layer protocols use. And in general, at a very, very high level, there are a few different things that that layer is responsible for. One of the most important parts is multiplexing, where when a machine is on a network, it has an IP address at the network level. That IP address in general is for that entire machine. Now, as we know, because we're in CS361, one operating system does not just run one program. It runs lots of different programs at a time that are probably trying to do lots of different things, and they probably all want to have their own conversations. Maybe one program wants to have multiple conversations itself, with itself, with other programs on the same machine, with other programs at different places within the internet. All of this is fair game. What we need to enable that is the ability to multiplex those different application layer messages onto a connection from one host with an IP address to another host with an IP address. And that's what port numbers are for. We have ports both in UDP and in TCP, which are the two most popular transport layer protocols. One provides reliable in-order byte stream service. The other provides unreliable datagram-based service. But they both provide this ability to multiplex across different processes or ports or connections, or however you want to use that concept of multiplexing based on an ID number. The next important thing that the transport layer allows us, as I was kind of alluding to, is to choose. Do we want to create an application where every single message that gets pushed in on one side comes out the other side, even if one of those messages got dropped the first time you tried to send it, even if one of those messages got delivered out of order, even if there are lots and lots of other users that are all trying to send at the same time, so I have to send much, much slower. These are all options that sound kind of, at first glance, like, yeah, why would I not want something to be reliable? Or why would I not want something to be in order? This is where we get one of these really, really great examples of an engineering trade-off. If we're trying to do something like watch a live football game, we don't want to, we could use a reliable transport layer or an unreliable transport layer to watch that football game. And if we were using the reliable approach, when packets get dropped, and remember, packets can get dropped all of the time, it's just a normal thing that happens, we can either slow down our live feed so that we definitely see the next message, or we can just say, you know what, show them blank or make it garbled or whatever, just don't waste your time trying to see something from 2 seconds ago. I want to see what's up to date live right now. You can imagine that if you're watching a live football game, you would far rather prefer that something is unreliable, but it stays up to date as long as it's reliable enough for you to get an idea of what's going on so you can know exactly what's happening, exactly when it happens. Whereas if you were, say, watching a TV drama that, premiered 2 years ago, it's not as important that you see it as fast as you possibly could, maybe with a few missing frames and all, but it's more important that you see everything in order. And if it buffers for a little while or it slows down for a little while, that's preferable to just not seeing what happened in one specific pivotal scene. So this is what the transport layer provides for us. And the most complicated and important and impressive part about this is the ability to create a reliable transport mechanism on top of an unreliable transport mechanism. We'll see a lot more about that in a video coming up soon about how we do distributed congestion control. So moving on to the network point of view, one really important thing about transport layer is that it's fundamentally about a sender talking to a receiver that are at two different places in the internet, and they're connected by some collection of routers that forward that message hop by hop by hop by hop. They have no concern about how that message gets delivered. They're just going to say, make it reliable, or they're just going to allow you to multiplex it onto different port numbers, whatever that transport layer protocol is meant to do. But now that we're down at the network layer, Here is where we actually have to go from one network to another network to another network to another network using routers to get a message from the source host to the destination host based on its destination address. There's two really important vocab words here, only one of which I have on the slide. And one is routing, which is effectively how do you decide what path to take to get from point A to point B for some specific destination B. Routing is this high-level decision about figuring out how you're supposed to get from point A to point B. Kind of an analogy I guess I could give is if you're using Google Maps to get someplace, you're going to punch in your destination and you're going to see what you're supposed to do, and you're going to see that entire set of turn-by-turn directions or whatever have you, and that's kind of doing routing. You're deciding what's the shortest path, and that doesn't get done all at once. One really important difference between Google Maps and the way the internet does things is that every individual router that makes a decision about where to send something makes a decision based on the information it has locally. Routers that are in the middle of the internet know how to get to every network within the entire internet based on whoever it is they're connected to. They might be connected to 2 other networks, they might be connected to 2,000 other networks, but they do have an idea based on all the IP addresses in the internet. I should send these to here, I should send these to here, I should send these to here. Figuring out what's the fastest way to get to an ultimate destination. If I want to get to this ultimate destination, maybe it's faster to go this way. If I want to get to this ultimate destination, maybe it's faster for me to go that way. That is the process of routing. You're figuring out what is the best path to get from where I am to a specific host. You could imagine that you only have to make that decision when the shape of the network changes, like if one router goes down or another router comes up or you get connected to a new ISP. Any of these things are going to make you say, oh, well, the shortest path is no longer this, maybe now it's this. That allows you to make those decisions at a relatively coarse-grained timescale. What we'll see next is that at the link layer, which is the next one in our 4-layer internet model, we're going to make hop-by-hop, message-by-message decisions every single time we need to forward a message. Another important capability provided by the network layer is naming at a global level. Every host that is participating in internet, according to the full and proper definition of the term, has a globally routable IP address. And that globally routable IP address should conceivably be reachable directly from everywhere else in the entire internet. There are a few exceptions to this rule, but in general, we're going to have this network layer be where we give individual hosts unique names. And because these are computer readable, they're going to be just numbers that get assigned to them. And finally, we have resource management. That's the other thing that the network is in charge of. And this is where we get best effort service. In a network where I'm receiving more messages than I could ever possibly send, and I don't have enough buffer space to hold on to all of them, I will eventually need to start dropping messages. And this is part of the standard of the IP layer of the internet, is to provide best effort service. It is going to try to send those messages closer to their destination, but that's the only thing that it's really required to do by the internet protocol, which kind of makes it pretty amazing that everything works even when it does work. The last layer of our 4-layer internet model is the link layer. So the link layer is what we're going to use to get from one point to another. So I have my super grody design here. This is topologically correct, but aesthetically horrible. If we have a source on one side, we have a destination on the other side. The routing concept is about how do I figure out how to get all the way from the source to the destination, even though I'm going to be making that decision hop by hop. Forwarding, on the other hand, is about specifically getting from one host within an individual network to another host in an individual network. This is the decision that's going to be made for every single message over and over and over again based on its destination IP address. Not only does the link layer provide this hop by hop message transmission over an individual network layer, it also provides framing, which is basically saying, how do we know when one message starts and one message ends? How do we know when one message ends and the next one begins? Things along those lines. The main thing here is that it's going to forward those messages. It's going to figure out how to send them to the intended destination. Another important thing about the difference between hosts and networks is that when a bunch of hosts are on the same network, they can kind of all directly speak to each other. In some flavors of networks, like switched wired Ethernet, you're always just using one medium, like that copper cable between your computer and the router. You're the only one using it. So you send your messages as fast as you possibly can. The router sends their messages back to you as fast as they possibly can. Nobody ever interrupts each other. But if we think about Wi-Fi or cellular networks, that's not the case. In a Wi-Fi network, it works just like a noisy classroom does. If two people try to talk at the same exact time, whoever was supposed to be receiving that message, whether it was one person next to them or the professor at the front of the classroom, isn't really going to be able to understand what those two people said at the same time. They'll have to say, hey, I didn't hear you. Will you send that back to me again? This is the basic concept behind media access control, where we say, let's set up a bunch of rules for how to be quiet, let other people speak, then we listen, then we wait a little while, and then we try to speak ourselves. In a classroom, we all kind of do this distributed algorithm for media access control without even thinking about it. We stop, we wait, we listen for a little while. If we start talking and somebody else does, we stop right away. If someone else starts talking, we want to say something. If we're reasonably polite, we're going to shut up until they finish talking and then wait a little while and send our own message. This is the basic idea behind media access control. But the point that I want to drive home here is that this is an important responsibility at the link layer. If I'm physically connecting with optical signals through glass or electrical signals through copper or radio signals through air, sometimes I'm going to need to share that medium with more than one other potential sender, and I need to find ways to share that effectively. There's a lot of different ways to share. We're not going to cover any of them in this class, but it's a really interesting aspect of networking. And finally, because we are doing this real physical thing of sending messages from point A to point B, the real world with all of its RF interference and kinked cables and other random things can come in and corrupt the messages that we're trying to send. So the link layer is one of the places where we're going to say, you know what, it makes sense for us to do error detection, maybe even error correction, to make sure that those messages get sent as efficiently as they possibly could. So we went over these 4 different layers of the internet model, and how are we going to actually implement these and make them a reality? The answer to that is encapsulation. We're going to put our application layer messages inside of transport layer messages, which are inside of network layer messages, which are inside of link layer messages. So in a popular, say an HTTP example, we can have our application layer message here at the top level. What we will end up with is when we send these individual link layer messages from one computer to another computer over a medium, they are going to include in them an IP header, and they're going to include in them a TCP header, and they're going to include in them some application layer message, which might even have its own header, which then gets concatenated onto some data that it's going to send. HTTP itself also has an application layer header that includes metadata, and then a body in some messages, and some messages don't have bodies. And those messages can be bigger than one individual packet, and so they have to be split along lots of different packets. So to see a really quick real example of how all of these different layers are put together, this is a recording of every packet that was sent and received by my machine to open the web page stored at http://example.com. So immediately you can see one important fact here. When I want to connect to example.com, I do not first make a connection to example.com because I don't know what IP address it has. All I know is that it's what a human typed in as example.com. And so I make a DNS request of my DNS resolver, and it tells me what the IP address is for that. In this case, my browser wants to see whether it should connect to the IPv6 version or the IPv4 version of this machine, and it chooses that it's going to connect on the IPv6 version, and it then makes a transport layer connection, it sends its request, it receives its response back, it actually makes a second HTTP request, receives a second HTTP response, and acknowledges all that. The important part here for our purposes for layering is that every single one of these messages is an encapsulation of all of these different layers that we were talking about. Even though here we're seeing that this is an HTTP message, and this is a TCP message, and this is a DNS message, every single one of these messages is an encapsulation. So in this instance, we have an HTTP message that's inside of a TCP segment that's inside of an IP datagram, that's inside of an Ethernet frame that was put onto the wire by my Ethernet card's driver. So you can take a little bit of a closer look here. We can see that fundamentally what we have is a whole bunch of bytes. On my local Ethernet, my machine sent all of these bytes to wherever it was going, to the local router. What this program Wireshark here does is really, really useful. It's one of the best programs you could ever get to know if you're going to be taking a course like CS450 or you just want to see how networking works. What this program can do fundamentally is it knows all of the protocols that are used in internet, and it takes these bytes and it turns them into human readable information, as we're seeing at the top of this window. For instance, the Ethernet header is just this information right here. Those all the way up through that byte DD. The internet protocol header is at 60 all the way through to 1946. We got the TCP header that picks up where the last one went off, dropped off, and it moves on forward to those collection of bytes. And then we got the HTTP header, and that shows us all of that encapsulation. So while we have this entire frame of a bunch of bytes that are packed in according to a set of rules, if we look at it the way that the computer understands it, all of these different layers, we see there's a huge amount of information, and each of these is being used in different ways to get the job of interneting done. So back here in our slideshow, we can see this is a slightly different way to look at and think about the TCP IP protocol stack. So when we talk about the internet and we talk about the 4-layer internet model, we're kind of implicitly talking about TCP specifically, so we're only going to be talking about TCP from now on. So there's a couple important things that I want to point out that are kind of subtle but really important about this slide. The first is that at the application layer and the transport layer, the only hosts that are involved are the end hosts that are involved in an individual conversation. This is a point-to-point from original source all the way to ultimate destination conversation. And while the routers in between are sending those IP messages that they're encapsulated inside of, they aren't looking at the application layer. They're not looking at the transport layer. All they're looking at is the IP layer to figure out where to send that message at any given point in time. So the network layer also kind of sits there in the middle between the transport and application layers as well as the link layers. And it's really there for getting a message all the way from the start all the way to the end and vice versa for two-way communication. The next most interesting part about this diagram, about this slide, is that when we get down to the lowest level, the link layer, each of these is their own individual network. And so they can be completely separate from each other and have completely separate technologies. And all they're there for is to get from one host to another host through a network. That's the only thing that they're necessary for. And they can be completely different from one hop to the next. That's another one of those flexibility arguments that is really important about how the internet works. So finally, there's this concept of the thin waist or in the internet's design, where the idea is if we put a few different really important but relatively minimal capabilities in that IP layer right there in the middle, we can build lots and lots of different applications on top of that relatively minimal set of guarantees. All we really want to do globally is make sure that messages can get closer to their destination and make sure that we know which destination to send to. So that's where we care about addressing and routing. And then we'll care about things like reliability or what application people want to use. So if you care about those things above that layer, the only places you need to implement your application layer or your transport layer stuff is in the end hosts. Likewise, by putting those globally routable things in a layer above the data link layer, we can use those completely different network technologies for any individual network that is being connected into the internet. This kind of really brings together all of these ideas and shows one of the most important concepts that went into making the internet as successful as it is. So this is really important. This is really awesome. This is really cool. And we have used layering and encapsulation to minimize the complexity that goes into making a functional internet. But that complexity still exists. We made it more manageable, but it's still there. So one kind of downside of this, of having all these different pieces, is that if any one of the relatively important parts falls apart, stops working, then your network is not going to work the way that you want it to. If DNS goes down, you can't use anything. If AWS goes down, so many of these different services online rely on services that come out of Amazon Web Services that a lot of the internet goes down too. There's lots of different ways that things can fail. And an important thing to remember is that if we had some big fancy integrated protocol, it wouldn't solve those problems. And there's no way around a lot of them. There's a lot of moving pieces that are here. And probably one of the most insidious parts of this layering model is that it's very hard for us to make really strong guarantees about the way that things are going to work. Because not only do we have to look at how each individual layer works by itself, we've got to learn how all of them fit together and better understand the ways that they'll fail and all of that. So this is all to say that the internet isn't always super reliable, but it is pretty awesome and usually works most of the time. And one of the most important reasons that that's the case is that we use this hourglass model, is that we used this concept of encapsulation to limit the complexity and tackle it in a way that has been successful so far. Thanks so much for watching, and I'll see you next time.